சார் நீங்கள் ஸ்டார்ட் பண்ணலாம் சார்.
நான் போர்டு கனெக்ட் பண்ணிடுறேன், ஒரே ஒரு நிமிஷம். ஏன்னா போர்டு வந்து நான் ஃபுல்லாவே டிவைஸ் மாத்திட்டு இருக்கேன் நான். Yes, sir, you can connect now.
ஸ்டார்ட் பண்ணலாம் சார். நீங்கள்
ஸ்டார்ட் பண்ணலாம் சார்.
சார் நீங்கள் ஸ்டார்ட் பண்ணலாம் சார்.
நான் ஸ்டார்ட் பண்ணிடலாங்களா?
ஆமாம் சார், ஸ்டார்ட் பண்ணுங்க சார்.
So, very good afternoon from India, and in this class we are supposed to cover probability and distribution. Strictly speaking, probability comes before distribution, and actually we go for testing and estimation after distribution. So what I plan is mainly to start with distribution, which is actually in between, and we will proceed downwards to get into some clarifications and problem solving techniques for probability, and mainly for and similarly for the case with testing and estimation also we require knowledge of distribution. So the plan is to start with distribution, okay, and gradually get into probability down the line, and in the higher order we will go for testing. Okay, so this is the base idea. So we will now start. I will share the whiteboard now. Okay, that's the idea. So can you see the whiteboard now? Is it visible?
இல்லை சார், எதுவுமே விசிபிள் ஆகலை சார்.
எதுவும் விசிபிள் ஆகல, ஒரு நிமிஷம். Is it okay now?
ஓகே சார். Okay, sir. Okay, sir.
Okay, this is okay now. Right, fine. See, to begin with, actually, as I was mentioning, when we say probability, okay, so it is actually it is associated with the event. Okay, it is associated with the event, and so we call that event as A. Okay, we call that event as A, and it is nothing but a measure of uncertainty over that event, whether it can happen, and if so, what is the degree of guarantee? Okay, so associated with any event, there is a unit of uncertainty. Say, for example, when we go for physical things like height, weight, we have certain units. So height is measured in meters or feet, and weight is measured in kilograms or grams. Okay, so associated with height, we have meters. So similarly for events, okay, we attach a particular metric which is called probability, and it normally takes values in between 0 and 1. That is the idea. Okay, so when it takes the value 1, we say that that particular event is bound to occur or sure event. Okay, we can say in this case it is sure event. Similarly, when the probability is equal to 0, we say that it is an impossible event. Okay, impossible event. So, and in between, okay, we have other combinations, right? It is very likely to occur, okay, then it is 0.7, okay, very likely, and when it is very unlikely, okay, it is 0.2, something like that, okay, very unlikely. So this is one area of one condition of probability or one assumption, so to say. Then we have certain, if A is a particular event, okay, it is taken from collection of events, okay, it is a subset of what is called collection of events. Okay, collection of, and the collection of events, okay, we will use the notation capital omega, okay, we will use the notation capital omega, and we can even put it like this is a collection of events, so to say, general, okay, and in particular we can say it is a subset, okay, that is so this is also called in sometimes sample space. This is also called sample. So, and as and when we come across certain concepts, as I was talking about in distribution, I think we will have this, because problem solving is most important, and some preliminaries, so to say. Okay, so this is as I said, measure of probability and certain things associated with the event, so to say. Okay. And we have other similar properties associated with probability that normally in any standard textbooks they are available. Say something like if A is a subset of B, then probability of A is probability of A is less than or equal to probability of B, and probability of the master set is always equal to 1, because one of the elements in the master set is bound to occur, so that has to be 1 surely. Okay, so this is the thing. Now, okay. So what happens with this is we will take up specific problems and start working. So as and when certain concepts are required in probability, okay, we will get to it. The very first problem that I am going to consider is, okay, so it is a question from 2019 first paper 1E, okay, 2019 first paper 1E, and okay, so the problem, I will write it here, okay, or I will go for the new screen better. So the problems, as I was mentioning, it is 2019 first paper statistics, and it is Q1E, okay, Q1E. It tells that x1, x2 and x3, they are 3 independent variables, okay, independent variables, of course random variables, with common PDF, and the common PDF is given by f of x is equal to 2 times e power minus 2x, x strictly greater than or equal to 0, 0, right? Otherwise, this is otherwise. So whenever we define a random variable, okay, so we should also be in a position to see whether what is the range in which it is defined, or what is the support. Okay, here the support is only the positive set of real numbers. Okay, positive set of real numbers. And what we are asked is, they are defining a random variable called y, which is nothing but minimum of x1, x2 and x3. Okay, this is the minimum of the random variables, and for this random variable y, okay, we are supposed to find MGF of y. First requirement is to find MGF, moment generating function of y, and then we are supposed to find 2 more things, which is expected value of y and expected value of y square. Okay, so that is the requirement. Okay, now what happens is, first we have to find the density of y then only we will be in a position to calculate the MGF. Okay, so to calculate MGF, we need to find the density of Y. So this is one idea, right? So this is minimum is the one that is very low. Maximum is the one that is the highest possible value. So in general, we can say ortho order statistics. Okay, in general, we can say ortho order statistic. Okay, so we take 1, 2, 3 up to n. Okay, and we order this into, this may not be in order. Okay, when we consider x1 random variable, x2, etc., xn, this may not be in order. So if we order it, so then we will write something like this: x1, x2, xn. Okay, and x1 being the minimum and this being the maximum. And what happens here is, in between also we have second order statistics, third order statistics, etc. So what I am going to provide now is a general setup so that you can use it even when the question is asked with respect to maximum, right? So if it is something with respect to R, okay, something with respect to R, and if I put R is equal to 1, it corresponds to our particular problem, this one minimum. And if you put R is equal to n, then it corresponds to a problem which is equal to maximum. So that is the way in which we will proceed. Okay. So we want to know the density of XR. Okay. We want to know the density of XR. So density of XR is, I will write it here. F of XR. Density is always written with respect to small f, and distribution is always written with respect to f. So we have n factorial divided by r minus 1 factorial and n minus r factorial, and then fx of x, and then capital Fx of x power r minus 1 and 1 minus Fx of x whole power n minus r. Okay, so this is the general structure. General structure. And in this general structure, as I said, if I want a minimum, in this case, what is my n? 3, because I am taking only 3 random variables. And what about my r? R is equal to 1, because I am interested only in the minimum. If it is the problem involving maximum, then it should be r is equal to 3. R is also equal to 3, n is also equal to 3. Or also take values 2. It is also possible that it can take the value 2. Okay. So now I want a minimum, which is x1. Okay, I will put 1. And if you put n is equal to 3, 3 factorial, which is nothing but 3 into 2, which is equal to 6, divided by r is equal to 1, then it becomes 0 factorial, which is 1, n minus r. Okay, and then I want this f of x. Okay, and that f of x is already given here, 2 times e power minus 2x. Okay, e power minus 2x. Now we have a choice. So we should either know that this is a distribution. Okay, this is a density from the distribution exponential. Okay, for which we have the distribution function. Okay, distribution function, which is nothing but 2 times, or this one f of x I am talking about. The distribution is given by 1 minus e power minus 2x. E power minus 2x. Okay, this is my and here r minus 1. R is equal to 1, so 1 minus 1, this is 0. And then we have e power minus 2x, which is 1 minus this. Okay, 1 minus this part will be e power minus 2x power n minus r. That means 3 minus 1, which is 2. Okay, that is the thing. Okay, so now we want to simplify this. Okay, we want to simplify this f of x. Either we can take it from the exponential distribution, or it's a matter of simple fact. We can integrate and see also. So I will also integrate and tell how that things are arrived. Okay. So I will go to the new board. Okay. So what I want, I will take up because that will be useful in my next board. So I am going to take this up, which is going to be used. Sir, whether the audio and whiteboard is seen clearly? Is there any issues?
No problem, sir.
Okay, okay. So this is what we have. This is what we have from the previous slide or previous board. Okay, so we can minimize this first of all. We can minimize this. So in the sense that we can cancel out. Okay, this is this 2 will get cancelled with this, and we will have a 6 from here. Okay, and these two things get cancelled, and then we have e power minus 2x. Okay, e power minus 2x, and here we have 1 unit, here we have 2 units, so put together we have power 3, and then this is anything power 0 is 1, so we can leave it as such. So this is what we have finally, 6 e power minus 2 into 3, 6x. Okay, 6x. So this is my density. Since x1 is denoted by y, now I can write f of y, and my f of y is now x replaced by y. Okay, y 6. Sorry, 6 e power minus 6y, and then what about my y? See, we should see what is my y. Y is minimum of some positive random variables. Okay, minimum of positive random variables. When each variable is positive, okay, and minimum cannot take any negative value. So my y is also non-negative. So this means this is greater than or equal to 0. Similarly, we can write 0 otherwise. Okay, 0 otherwise, which is a standard notation we use. Okay, so this is a bracket-like thing. Okay, now what we have is f of y power this density we arrived at. Okay, this density we arrived at, and as I was mentioning, the only issue is with respect to the distribution function that we assumed. Okay, distribution function that we assumed. Okay, that distribution function we can derive it side by side. So what we had is fx of x, which is nothing but 0 to, actually it should be minus infinity to x, but since this being a positive random variable, I can start with 0. So 0 to x, okay, and my density is, as I know, it is 2 times e power minus 2x, but since I have x here, I will put it as y dy. Okay, this is a simple integration which we can do quickly. Okay, e power minus y divided by minus 1. So I will interchange the limits. Okay, strictly speaking, I should include minus 1 and put the limits, and then I can interchange. So minus 1 is absorbed if you interchange the limits. So 0, 1, and anything power 0 is 1. Okay, this is the x actually. This is x, and we will have e power minus x. Okay, we will have e power. Okay, so 1 second. So we have this. There is a 2 here. I am missing everywhere. There is a 2 here. So I will put it separately. Okay. So then what will happen? I will have a minus 2 here. Okay, I will have a minus 2. This is 0 to x, and this minus and this things will get cancelled. E power minus 2y. I will have now when it is interchanged, it is something like this. Getting to 0 becomes 1, and then e power minus 2x. And this is what I substituted here. Okay, this is what I substituted here. So it's a simple derivation only, but the thing is that if you are comfortable with the exponential distribution, once you know the density, you can directly write the distribution. If you don't know the exponential structure or see the things associated with the exponential distribution, then also, as I said, you can side by side you can derive it. It's not going to take much time. Okay. So since this is 1 minus f of x, this f of x is 1 minus this, 1 get cancelled, minus will become plus, and we will get this. So in a way, we have justified all the terms in the components. Okay, having derived the density, now we will go for MGF, moment generating function. Okay, this is called the moment generating function. Moment generating function. And why we have this name is, once we derive this function, okay, we can differentiate that function once substitute t which is equal to 0, that will lead to first moment, which is e of x. Okay, that is the idea. So parallelly, we can also have some properties associated with MGF. MGF is actually defined as notationally mxt. It is the variable because only associated with random variable we can define MGF. Okay, it is not with any other concept. Given a random variable x, we can define this. And how we define this? It is nothing but expected value of e power tx. E power tx. E is actually our Euler's constant. Okay, and when this expectation exists, then that function is the function of t, because expectation means integration or summation over x, and that x will get integrated out or summed out. So ultimately this will become a function of t. So that is the idea. So we have this ultimately a function of t. That is why in the main argument we put t, and x is something like a subsidiary. We cannot even call it as argument. All that denotes it is associated with the random variable x. So now we will put it like this. So, and what I said was something like, if this is my moment generating function, mxt, if I differentiate once with respect to t, and I put t equal to 0, it will give my first moment. Similarly, when I differentiate it twice, mxt divided by dt square, when you differentiate twice with respect to t, and then substitute t equal to 0, it will give my e of x square, and so on. Okay. So since this is first order moment, this is second order moment, as this function under differentiation and substitution generates different orders of the moments, it is called a moment generating function. Okay? So that is one way, and it reduces a task very to a great extent, in the sense that otherwise what happens is, see, you can imagine when an integral is with respect to x into that density. When it is x square into the, when the order of the moment increases, the integral becomes very difficult. In a way, that is the main reason why we use MGF. It is immaterial because differentiation is somewhat simple compared to integration. We can differentiate any number of times, and we have also some rules associated with the nth order integral. Nth successive integral, so to say, nth successive differentiation. Whereas there is no such thing called the nth successive integration. So in a way, that is what we are indirectly exploiting here. And we can see that we want now e of x first. First we will generate the moments. Moment generating function, as I said, this is equal to expected value of dx. And how we define expected value? Because x is a continuous random variable, it is an integral, and over 0 to infinity the range. And this is given by f of x, already defined there, and e power tx, whatever we have there, into f of x dx, the density. And that is equal to 0 to infinity. And that is equal to 0 to infinity e power tx. And what about your f of x? And your f of x is now 6 e power minus 6x. I am translating in terms of x, that's all. Already we have defined it to be y. So I will put it like this. So we had it already here. The same density I am using. The same density I am using with respect to x, nothing else. So now we will continue with this color. So this is equal to, this is equal to, so we have this density with respect to x dx. Or if you put y, it is, see whether this x dx or y dy, it is going to have only a dummy effect. It's going to have only dummy. So you can see here, simply I will put it something like that. X square 0 to 1 dx. Ultimately this is going to be x cubed by 3, 0 to 1, which is 1 by 3 minus 0, ultimately 1 by 3. Even if you put something like 0 to 1 y square dy, ultimately it is not going to matter much. We will get y cubed by 3, 0 to 1, which is also equal to 1 by 3 ultimately. So whether it is x square dx or y square dy, it doesn't matter. Only the structure of the function matters. That's why normally an integral is always said it is a function of its limits. Even though we have integrand and other things to be integrated and substituted finally, what matters ultimately is it's not the variable. It's in a way also called dummy variable. So we have that limits that is going to decide the things. So here I am not changing any limits, only the variable. Now we have something like we can take 6 outside. And then integral 0 to infinity. And then we have e power see how I am slightly rearranging this. So I want this something like 6 minus t into x dx. Okay, 6 minus t into x. This is minus 6 of x plus tx. So I can even write simply t minus 6. That is also possible. But what makes here more different is, see, this integral is well defined only if your t is less than 6. Your t is less than 6. And of course, you can have t to be greater than 0 also. Because when t is greater than, t takes negative value, okay, t takes something like a negative value. So then it will become positive. Okay, then we have some integral convergence issues. So when t is less than 6, what happens is we will get a positive value inside. Okay, and when it is positive, okay, outside is negative, so e power minus integral converges. E power plus x we cannot integrate directly. E power plus x we can integrate, but only within finite limits. So this is an infinite integral. So convergence issue comes, limit issue comes. So we should be very careful about it. Even it can take negatively, that doesn't matter. As long as it is less than 6, okay, it is well established. It is, the convergence is guaranteed. So we will take this integral to the next slide. So I will take this part. We will move to the next slide. Test 3. Sir, any audibility or drop in the whiteboard vision? Okay, please let me know. I hope this is going okay. So we have this. Okay, this is what we had it in the last. So this is what we are supposed to integrate. Okay, so I will use it directly, which is equal to, okay. So we can take 6 as such out. Okay, so this is something like e power minus t. So e power minus 6 minus t into x. Okay, divided by same concept, minus t 6 minus t. Okay, it is something similar to this, e power ax. When it is integrated, we have e power ax by a. Okay, the same concept I am using here, the same concept. Okay, and of course I have to substitute the limits, which is equal to 0 to infinity. Is 0 to infinity, which is equal to. So now I can make certain adjustments. Since integral is done, okay, I can interchange the signs. Okay, no problem. See, it is the power of e power x that matters actually. Okay, so now I can take it as something like t minus 6 in the denominator. Okay, t minus 6, or even better, I can have it 6 minus t. Okay, I can have it 6 minus t. I will interchange the limits for this minus sign. So I have something like e power minus t minus 6 minus t, 6 minus t, okay, into x. Okay, I will interchange this 0 to infinity to 0. So what will happen is 6 divided by 6 minus t. And then when I substitute 0, okay, when I substitute 0, what will happen is e power 0, it will become 1. And when I substitute x is equal to infinity, e power minus infinity, it will become 0. It will become 0. So ultimately, I will have my mxt, moment generating function, as 6 divided by 6 minus t. And I should say that this is valid for t less than 6. Even t equal to 6, we will have an issue. The denominator 0 is never allowed. Okay, after getting this, okay, we can go for what is called how to derive e of x. Okay, expected value. This, as I said already, you differentiate the mgf with respect to t. Okay, and substitute t equal to 0, which is equal to, your mgf here is d by dt. Your mgf is, now only we derived, it is 6 minus t. Okay, It is something like your value appearing in the denominator. It is something like 1 by x, differentiation of this is 1 by x square, right? So we will have minus 6 divided by 6 minus t whole square, and under the value t equal to 0. Okay. And when I substitute t is equal to 0, let me see what happens. When I substitute t equal to 0, this will become 6 square. Okay. One second. We don't have this minus here. It's not. Sorry. One. I'll put it like this. So, yes. We differentiate once. Okay. This is minus 1 by x square. And within this integrand, okay, within this differential, I have to introduce a minus sign because there is a minus t. And that minus will get with this minus cancel. So I am not cancelling because that will remove the effect. So I will put minus sign here, again one minus sign, okay, so that minus into minus will become plus, and I will have 6 by, when I put x is equal to t equal to 0, this will become 6 square, which is 36. Ultimately, this value is 1 by 6. Okay. So for f of x, for e of x, so my value now is 1 by 6. So that is the e of x. Now what I am going to do is, I will proceed with finding the value of e of x square. I want e of x square, which is equal to, I have to differentiate twice. That means I have to differentiate already what is being differentiated. Okay. So that means d by, strictly speaking, d square by dt square mxt. Okay. But since I have differentiated and I have the value already, so what I suggest is I can differentiate once, or which is already differentiated. Okay. So the what about which is already differentiated value? That is what we have here: 6 divided by 6 minus t whole square. Okay. And this is what has to be done. 6 is a constant we can take out. The value that we have is something like 1 by x square, which is supposed to be differentiated, which is nothing but minus 2 by x cube. We can use the power rule also. We can take the power to the numerator. We can have it as something like x power minus 2. Under differentiation, this becomes minus 2 x power minus 3, which is same as n x power n minus 1. Okay. So when this is my constant I have as such, and as I said, this will go to the numerator with minus sign, and 6 minus t power 3, and there is one minus sign. Okay. So put together we have something like this: 12 divided by t 6 minus t whole cube, and we want this at t equal to 0. That means, which is nothing but, we have something like 12 divided by 6 cube. 12 divided by 6 cube. When t is equal to 0, 6 cube, this becomes 6 cube. So this on simplification, okay, 1 6 will get cancelled with 1 6. We have 6 square, and we have 1 6 with 2 cancelling. We have something like 1 by 18. Okay, 1 by 18. So the requirement is we need to find what is x square, e of x, and what is e of x square. Okay, e of x, as I said, it is 1 by 6 already given, and now we have 1 by 18. And see, it can also be indirectly put like this. Instead of asking you separately what is e of x, what is e of x square, they can simply ask what is v of x or variance of x. Right? That is also a possibility. So in that case, this way they can indirectly ask, right? It is not that you should differentiate once, get the value of e of x, and differentiate twice, you should get the value of x square. So you can indirectly, if it is asked with e of x, v of x, okay, it is one single way of requirement, okay, which needs to carry out all these things. Okay. So if there is any questions, I am ready to answer. I think it will be posted in the chat and it will be routed to me as it seems. Is it not, sir? So anybody there coordinating?
No question, sir.
Okay, fine. No question coming in the chat, right? That's what you mean. Okay, fine. So we will continue. So I will take up the next problem. So let me save this. We will go for the new go. So here, what happens is the next one. Okay, the next problem is the problem connected with 2008. Okay, the next problem is the problem connected with 2018 2A. Okay, so this is coming from a paper 2018. Question number 2, subdivision E. Okay, this is again a problem dealing with the continuity of continuous random variable, and the problem is you have been given continuous joint density of the two random variables f of xy, which is e power minus y, and your range is because it is x and y, we have to define the where it is defined. Okay, it is something like 0 less than or equal to x less than y less than or equal to y even. Okay, less than or equal to x less than or equal to y, which is strictly less than infinity. Okay, this is how this is defined, and 0 otherwise. Okay. Okay, so this is how we have. So what happens is, what they require now is you are supposed to find marginal distributions of x and y. Okay, we are supposed to find one marginal distribution or density, marginal density of x. Similarly, marginal density of y, and then the next one is conditional density. Okay, conditional density. Conditional density of y given x. Okay. See, why I have selected this problem is, see, you can see here having two variables, right, x and y. It is a bivariate joint density. But if you see the structure of the variable, the structure of the function as such, okay, you can see no x appearing in the function. Though it is mentioned here something like it is a function of x and y, okay, it is a function of x and y, okay, when it is defined in terms of x and y arguments, but the function does not contain any x. So this is the very beautiful thing that ever happens. So we define a function in two arguments, but the function contains only one variable. So where does that x go? Okay, where does that x go? How that x is related to this function? So we know this is a function related, as per the thing, we know it is related to y, and see y x comes, okay, x comes in binding your y. Okay, y cannot vary independently from 0 to infinity. There is a lower bound x. So in this way this appears. So going by the functional structure, we cannot say that this is going to be a function which is independent of x. Okay, you should not see the function as such. You should also refer to the domain where it is defined. So our x gets into the function indirectly by its domain by controlling the variable y. When it influences y, automatically this also becomes a function, okay, of y. Because when a function, when we say it is a function of x and y, so changing the values of x and y should change the value of the function. Okay, so here it's indirectly it may not look like this involves the x, but as I said, it is there in your domain. It is there in your domain. Okay, so that is a very, very subtle point, because when we don't have access to x, see, what is your marginal density? Integrating joint with respect to y. What is your marginal density of y? Integrating joint with respect to x. If you want x, integrate with respect to y. If you want y, integrate with respect to x. But the problem is the function has only one y. Okay, we don't have any x as such. So how to deal with this? That is the crux of this particular problem. Once we get, I think this problem carries 20 marks. Okay, though it is a very simple, given in 2 lines. Find the marginal and conditional densities of. So these are that signifies its weightage. Okay. So to start with, first I will get marginal of marginal density of x. Okay, marginal density of x. Okay, so I will select okay, marginal density of x is integrate joint density with respect to y. So that is the idea. And since it's the integration is with respect to y, it is only a single integral. Only in when we need to verify whether it is a proper density, we need to have a double integral f of xy dx dy, and which is equal to 1. Okay, this is where it comes. But here we have only one integration, which is equal to integral, okay, e power minus y, okay, dy, and we want to know what is the range of y. Okay, we want to know what is the range of y. So range of y is you can see that it is from x to infinity. So it can lower limit x, it cannot go beyond x, below x, and it cannot go above infinity. Okay. So see, you can see this is also justifies what we said in the beginning. Yeah, integral is a function of its limits. Okay. So here, though we have y, ultimately it is going to be a function of x. So here also we say which is marginal density. So I can use the notation fx of x equal to fx of x is equal to. Okay. So this ultimately this is going to be a function of x. Okay. See, we have a joint density which does not even have x, but on integration, okay, it leads to a function of x. That is the beauty. So what about this value? As an ordinary integral, e power minus y by, strictly speaking, I should write minus 1. I will interchange the limits. So x to infinity, which is nothing but your e power minus x. And e power minus infinity is automatically 0. So now I got the marginal density. Okay, marginal density of x, it is defined by e power minus x. And now what about the range of x? We don't have any y, which is only marginal with respect to x. So now x can vary from 0. Okay, this is the starting point, and it can go up to infinity because there is no y now. Okay, there is no y governing at the upper level. Okay, so because it is a marginal, we are interested only in x. We are least bothered about what the y takes. So it is independent to vary in between 0 to infinity. So this function is valid for x in the interval 0 to infinity. Okay, and as usual 0 otherwise. Okay, we can have it separately. Okay, so similarly we want to find because here we have y. Okay, for y we may not have x. Okay, that may look like somewhat odd. Okay, so now I want to get the marginal density of y, marginal density of y, which I will denote it by fy of y, and this is got by integrating f of xy with respect to x. Okay, and now we know what is f of xy. It is e power minus y, and now with respect to x dx, and I want to know how this x varies, because then only I can write the upper limit and lower limit for x. See, now we come and see here x. Okay, and x varies in between 0 and y. Okay, x varies in between 0 and y. Okay, so it is 0 here, y here, so which is again equal to, so we can write this as e power minus y is taken out, remember, because my variable of integration is x. Okay, and the integrand is not involving any x, though it is y, as far as x is concerned it is going to be a constant, so I can take it out. So e power minus y, simply I have dx. Okay, integral dx is x. Okay, and it is from 0 to y, so which is nothing but e power minus y, and we have y minus 0, which is simply y, or to put it safely we can write y e power minus y. So now my marginal density is, so I put it here, fy of y is, marginal density of y is y e power minus y, and now see, being marginal, what happens to y? There is no x, so that is again can vary from 0 to infinity. Okay, that again can vary from 0 to infinity. That is again, okay, that is a possibility. So what we have is, we can say that y ranges from 0 to infinity. Y ranges from 0 to infinity. Okay, otherwise, 0 otherwise as usual. Because we need to define the things on the whole real line. Okay, when a random variable is defined, we should either tell where it takes probability and where it does not. Okay, otherwise it is some implied understanding is the points wherever it is not defined, automatically it assumes 0. Okay, that is another way of putting it. So now I have joint density and two marginal densities. Now I can find the conditional density. Okay, now I can find the conditional density. me save this first and proceed. So already I have 125. Okay, now we have a new board. Okay, so what is my joint density previously? It was given in the problem as such. It is nothing but f of xy, which is e power minus y. Okay, e power minus y. And what about the marginal density of x, fx of x? We derived it to be e power minus x. And we should be very careful about the range 0 less than x less than infinity. What about marginal density of y? Which is nothing but y e power minus y. Again, y is greater than 0. Okay, so this is the. Now we want conditional density of y given x. Okay, conditional density of y given x. There is a different notation, so we should be very careful with respect to the notations. Argument is y, but the variable is y given x. So better representation is something like this. Y given x represents the random variable, conditional random variable. The argument is y, because we want something connected with y under the condition that x is given. Okay, under the condition that x is given. That's how we should look at it. So this is nothing but joint density divided by marginal density of x, fx of x, which is equal to, provided your denominator exists and not equal to 0. That is also there. So we cannot arbitrarily place two values and say this is going to, and we should be a little more careful about functions. If it is numbers, we may be exactly knowing whether that value is 0 or not. When it is function, it is implicit. Okay, at some value it may exist, at some value it may become 0. So we should be doubly careful when we have functions in the denominator rather than numbers. That is one thing. Okay, we should be very careful. So we have e power minus y in the numerator, and in the denominator e power minus x now we have. So now my function becomes e power minus y plus x, or safely as in the previous case I can put it something like e power minus of x y minus x. That is a better way. Minus of y minus x. So why I require is, it is something like e power minus ax, a is greater than 0, has got some nice properties like integrability, convergence, everything. Whereas if it is purely a function of here also we have to define what is the range of your y. Okay, what is the range of y? See, here you cannot tell that y can vary independently of x, because it is y given x. We should be very careful. See, what is our f of x y? My f of xy is defined as e power minus y, 0 less than or equal to x, less than or equal to y, less than infinity. So previously, when I consider marginally with respect to x, okay, I never bother about y, so I said x varies from 0 to infinity. Similarly, when I consider about marginally y, I said I don't need to consider x, so it varies from 0 to infinity. So both marginals vary from 0 to infinity. Now I am not consider. I cannot say I am going to ignore y, or I am going to ignore x. So when I consider distribution of distribution of y given x, okay, so here you can see the distribution of y given x. So it conditions, okay, it conditions. I am interested in the variable y, but that variable cannot go below this x, because now it is governing, conditioning, right? So now we can say this function is defined not for everywhere. Okay, this function is defined not for everywhere. So my y, okay, it takes always values greater than x, greater than or equal to x, okay, and 0 otherwise, 0 otherwise. So, and also if you can verify by integrating this with respect to y, that is also possible. So you can take, you see, finally we say something like fy of x. Okay, we say something like fy given x of y, conditional density is something like e power minus of y minus x, and it is defined in the range y is greater than or equal to x. Okay, 0 otherwise. This is also conditional density is also a random variable. Okay, that can be quickly verified, because in some cases if you have excess time, okay, normally that we may not have the competitive exams, but still, if you have some time to, if you have some buffer time to verify what you have done, if you want to be very confident or maybe going for other questions, something of this way, you can quickly integrate this. So what will happen is e power minus y plus x, and this is a function of y, differentiate with respect to y. As when you differentiate with respect to y, e power x is constant, we can take out, and this is from x to infinity. Okay, this is from x to infinity. And what happens? E power minus y divided by minus 1. I will interchange the limits. It is x to it is infinity to x instead of okay. And we have e power x. Here we have e power minus x. E power minus infinity is 0. So e power x plus x, e power minus x get cancels, and e power 0, which is equal to 1. So we can quickly check also whether this is a proper density, because it's not there as such. It is required for the problem solving, but it guarantees that whatever that you have arrived at, okay, that is going to be the correct answer or safe answer. Okay. So I think this is what we have it in this problem. We think I will take up one more problem with the time limit. Okay, direct probability problem. Okay. Now, can you tell me if there is any question in the chat or otherwise? Please. Do you have the chat? Any questions appearing in the chat?
No, sir.
Okay, then I will go to the next problem, right? Okay, fine. So the next problem I am going to consider is taken from the year 2000. This corresponds to the problem. Let me first change the board. Okay, so we will go to the new board. Fine. So the next problem is okay. It is from, I will put it like this. (2018) 1A. Okay, it is taken from the paper 2018, and then 1A. Right, it is from the first paper. Right? So probability and distribution are both are dealt in the first paper itself. Right? So the problem goes like this. I will read it, and then I think we can start. We have a bag with 3 coins. One of them is a fair coin, but other are biased trick coins. When flipped, the 3 coins come up heads with probability 0.5, 0.6, and 0.1 respectively. If one of these coins is picked up at random and flipped 3 times, subdivision 1, what is the probability of getting head, tail, tail? Second subdivision, assuming that head, tail, tail occurred, what is the probability of having chosen a fair coin? Okay, so this is the question. Okay, so I will put it like this. So we have a bag, okay, in which we have 3 coins. Okay, coin 1, coin 2, coin 3. Okay, and one of them is unbiased and other 2 are biased. Okay, what do you mean by coin being biased or unbiased? If it turns out or gives equally likely the head and tails, it is going to be your unbiased coin. Okay, when heads and tails have equal chances of occurring, that is 0.5, 0.5. Okay, then it is called unbiased. So the first coin is unbiased because chances of occurring head is 0.5. It is given. What about the other 2 coins? They are biased. And what about the degree of bias? Getting head in the second coin is it is given as 0.6, and getting head in the third coin, okay, it is given as 0.1. Okay, fine. Now, what is your first subdivision? You take one of the 3 coins randomly, okay, and check what is the probability of and toss that randomly chosen coin 3 times and see what is the probability of getting a head followed by tail. So first subdivision is this. Yeah, we will go to the second subdivision as and when it comes. Okay, I will take a separate. So I have a structure like a bag containing 3 coins, of which one is unbiased. Okay, and which is unbiased? So this coin is unbiased because of this probability, and this is biased, and as well as this is biased. Okay, because not equal to 0.5. It gives second one gives more chances for heads. The third one gives very little chance for the head. So anyway, as long as there is no equal chance, we call it as biased, and it is absolutely immaterial whether it is biased little or biased more. Okay. So now we want to find the happening of HTT. First one, I will select one of the coins from this randomly and toss it thrice, and it so happens I want to get the probability.
Okay, sir, you can continue,
Yeah,
sir.
fine. Yeah, I'll find it. So we are talking about the thing that taking one of the 3 coins and finding the probability that this particular sequence happens. So in how this can happen? I can select any one of the 3. So each coin has probability 1 by 3. So I can select first coin for which the probability is 1 by 3. Once this coin is selected, I should get a head followed by tail. But here, getting a head, getting a tail, they are equal. Okay, so this is the chance. Okay, this is one possibility. Plus, I can get the second coin. Okay, and what happens if second coin is selected? Selection is 1 by 3 only because the random selection is going to be made. And getting the head is first one is 0.6, and I should get a tail. When getting a head is 0.6, getting a tail is 0.4 into 0.4, right? It is the complement. Okay, so it is something like when we have 70% chances of rain. Okay, 70% probability of rain is 70%. So probability of no rain is 30%. Okay. Similarly, getting head is 0.6, getting tail is 0.4. They should add up to 1. And what about the third one? There is a chance of 1 by 3 getting the third one. And if I get the third one, what is the chance of getting head, tail? Getting a head is 1.1, sorry, yes. And getting a tail is, in this case, 0.9 into 0.9. Okay, so I will quickly bypass the adding multiplication thing, okay, that you can do it manually, okay, or even you can use calculators and other things, okay. I will, we don't want to waste time here. I will directly write the number. It's a simple multiplication and addition, okay. That finally reduces to 0.10067. Sorry, 0.667. Okay, 667. You can verify this. You can verify this later because we are running short of time. Okay. Now, so this is the logic. Selecting one randomly, okay, for which the chances, say 1 by 3, 1 by 3, 1 by 3. That is how we have here. And having selected a particular thing, okay. So we have having selected a particular thing, we have something like the value that is being multiplied. Okay, so we have head, tail, tail. This is for your head. The first thing everywhere, okay, it is for head, and the second and third thing, tail, it's going to be repeated. That's okay. Now the second one is more complicated. The second one is more complicated in the sense we are not going to find the probability directly, okay, of this particular event. What they say is you assume that this has happened, HTT has happened. You assume that you have selected randomly and you have got the selected coin is tossed thrice and you got this event. Okay, what is the chance that you might have selected 1 because coin 1? See, there is every possibility that you could have selected 2 and got the same thing. You could have selected coin 3 and the same output. So in all cases, okay, we have both probability of getting head and tail. So it's not at all a matter. Okay, so all that matters is this happens with very high probability for which particular coin. Okay, that's what we are going to say. This is something like a conditional probability we have. Probability of A given B, which is defined as probability of A intersection B divided by probability of B. That is how we define. Okay. So in this case, we have this something like probability of selecting coin 1, okay, and getting head, tail, tail divided by probability of head, tail, tail. Okay. And this, see here we can put it, see here conditional probability is defined in terms of joint probability. We can put it also the other way. Okay, that is A intersection B can be written as probability of A given B into probability of B. Also this can be written as probability of B given A into probability of A. Okay, both ways. I want two things to happen. In one case, I assume that first thing happens and then the next one, what is the chance, and vice versa, right? So here what I suggest is, here I can use the conditional probability that C1 happens and probability HTT given C1, okay, divided by probability HTT. So what is the numerator? Given that coin 1 selected, okay, what is the probability of coin 1? Because it is randomly selected 1 by 3. And what is the once coin 1 is selected, what is the chance? It is the first case, okay. It is the first case. So this one. Okay. So in this sense, what we have is something like the numerator. 1 by 3 is this one. Okay. And once it is selected, what is the probability? 0.5, 0.5, 0.5, which is 0.5 cube. Okay. And what about the denominator? Denominator already we have calculated previously. Probability of HTT, which is nothing but 0.100667. So you can simplify this numerically, and this reduces to 0.413907. See, the idea, the entire thing, the idea is called, is developed by one statistician, Bayes. Okay. It is also called Bayes theorem. Okay, Bayes theorem. So it actually deals with conditional probability. So what he said is something like this: instead of dealing with the probability directly, you can deal with probability given some condition. Okay, given some condition. Normally this happens. See, what is the probability of raining? Given that it is a month of December, it is very high, or relatively high. given the month it is April or May, in India as far as I am talking about, and particularly South India, when it is March, April, May, the probability is very less. So normally one information we have, okay, what is the month, okay, what is the corresponding month. So given month, okay, the probability of raining changes. So it's always better to deal with probability of conditional probability rather than unconditional probability, because when we are supposed to find the probability, at least some related information is known. Why don't we use it instead of say something like making the event very arbitrary and putting the things like that. Okay, that's the main idea, and this idea is actually extended, and now it has been there is a separate school of theory called Bayesian inference. That is called Bayesian inference. That's called Bayesian inference, and this Bayesian inference, okay, it's a separate school of thought which actually makes conclusion not based on simple probabilities and parameter inference. Okay, it uses the prior information. Normally, any process only at the beginning stage it will not have any solid base. Okay, once the process gets going, okay, so we normally expect the past information to influence the future information. At least the immediate past has got more relevance. Okay, it's going to impact more rather than the distant past. Okay, that is also there. So that kind of making use of the available information to improve the prediction probability. See, probability actually means if you are predicting the event with some certainty or uncertainty, so to say, they are equivalent. Okay, once occurrence probability is known, okay, we equivalently it is said that unoccurrence is also known. Okay, one minus that. So it has got a very big application in many industries, particularly insurance industry, because unless we predict okay, what is going to, whether the person is going to met with risk, okay, and the risk may be anything, accident, death, disease, anything, right? So we are going to pay the premium, and to fix the premium we should know what is the probability level of the risk. Okay? For high risk we have to fix high premium, and for low risk we have to fix low premium. This is the obvious thing, but how high, how low, quantitative. So that is decided by such theorems, which ultimately the conditional information is the condition on the person's age, person's health, already existing information about the person. Okay, it is something like A given B. B is your age, gender, certain disease or gender specific, certain diseases or age specific, which normally occurs 40 plus, okay, or 50 plus or 70 plus. Dementia, Alzheimer's. So all such diseases, okay, they are not independent of age. Though there is no, solid scientific or clinical evidence that it should not happen at lower ages, but the predominant phenomena is that it occurs at higher ages, so probably around after 60 or 70. Okay? The onset may be a little bit earlier, that is a different thing, but the symptoms gets pronounced, and the difficulties of the person and also the person who is handling, okay, they are specially trained for coping abilities. And as I said, in the case of insurance, okay, this is a dissertation about the probability of risk, because if you are going to have a correct estimation based on which you decide a premium, your competitor is going to come to very close and give a competitive premium which will attract the customers. Okay, so it is not that high or low. Actually, what it actually matters is how high or how low. So that quantitative inference is got only by using these kind of information and nothing else. And when it comes to quality control, as far as the industry is concerned, okay, we cannot go and check each and every item, okay, when what all the company has producing. Okay, so we have to take a sample and check the quality, and we have to generalize, for which again we need the probability concepts. So if this is the chance of getting error in this particular batch of production, what is the chance that this much of or this proportion of default or substandard product has get into the market, something of that sort. Okay, so whether we can pass this to the market or whether we can recycle it and we can make it a better production node. Okay, so quality control is a decision making thing, for which again we have to use the concept of Bayesian approaches. So also in clinical research, okay, in clinical experiments, okay, So everything is conditional only. Everything is conditional. So as I said, given for this particular age group, for this particular gender, this may be the dose which works at the optimum level. And for different given conditions, a different level may be there. So it is gender specific, age specific, race specific. Okay, there are very many factors. Some of which are socio-demographic, some of which are even clinical. A person with a high BMI, body mass index, he will have different cutoff levels. Okay, we cannot say that this dose is going to work very well for all people. Okay, so there is no something like a uniform guarantee. It goes with condition on BMI, condition on diabetic status, condition of cholesterol level. Okay, so in clinical industry or pharmaceutical industry, this kind of conditional probability, okay, it plays a very major role in deciding the optimum level of dose fixation, which in turn actually decides the production cost, and which again decides in turn the cost of marketing. So and it's a vicious circle. Okay, the price. Okay, if it is going to be less, more demand, more quality. Okay, again and again. Okay, so in this way, I think we can make use of probability in a more optimal way, and it is at one end it has got very interesting solving characteristics, some such things, but it's not actually hidden tail actually that matters. It's only a symptom. Okay, it's only a model that we have. See, in case of quality control, whether the product is good or bad, that is equivalent to head or tail. In case of premium fixation by insurance companies, whether the person met with risk or is not going to meet the risk. Okay, so meeting the risk or not meeting the risk, one is head, another one is tail. Disease occurrence is head, non-occurrence is tail, or the other way. And having known having disease has occurred, what is the chance he will live or die? Okay, conditional probability. So it's a matter of a representation when we come to represent certain problems using probability with hidden tails. And strictly speaking, it can be generalized to, as I said, any industry like quality control, clinical medicine, and industrial production, industrial process control. And as I said, survival analysis is a separate field which uses probability. And there are very many fields, Okay, so probably how much time I am left with? Can anybody guide me?
Sir, time already over, sir.
Okay, shall I finish it?
Yeah, sir, you can finish it.
Okay. Thanks for watching, and if there is any question, I am ready to answer. You can put it in the chat box. I think that will be routed through some medium. Okay, I am ready to answer. If there is any question.
No question, sir.
No question?
Yes,
no
sir.
question, sir? Okay, I think then probably I think I can wind it up now. If even if there is any question at later stages, I think you can mail me. Okay, probably my mail ID may be shown to the it may be flashed so that I think you can mail the questions, okay, and get the answer. Okay. Okay, I will finish it. Thanks for watching, and all the best.